Hello friends, I am Chandan. Today's topic is heat engine, refrigerator and heat pump. Today I will calculate the efficiency of heat engine and COP of refrigerator and heat pump. So first consider heat engine. So heat engine concept is coming from Kelvin Planck statement. This heat engine concept is coming from Kelvin Planck statement. Kelvin Planck statement. That is second law of thermodynamics. Okay. So first consider this is source and the source temperature is T1. Now consider there is another observer, that is another reservoir, that is sink. The temperature of this sink is T2. Okay. Now in between source and sink there is a heat engine is there. Heat engine. Okay. Now this heat engine absorb some amount of heat from this source. Suppose Q1 amount of heat is absorbed from this source to this heat engine, and it rejects some amount of heat to the sink. Suppose this is Q2 and it is produce some work, that is W. Okay. So first consider this is heat engine. So what is heat engine? It is the cycle or engine that convert partial amount of heat into the work. So first, what is heat engine? It is the cycle or engine that convert partial amount of heat into the work. So what is T1? T1 is the absolute temperature of source. Absolute temperature of source. What is T2? T2 is the absolute temperature of sink. What is T2? Absolute temperature of sink. This is Kelvin and this is also Kelvin. What is Q1? Amount of heat absorbed by heat engine. Amount of heat absorbed by heat engine. What is Q2? Q2 is the amount of heat rejected by heat engine. Okay. So what is W? W is the amount of work produced by heat engine. So amount of work produced by heat engine. Okay. So now we derive the efficiency of this heat engine. So efficiency, that is eta. So efficiency, we calculate the efficiency, that is eta. That is the formula, that is output by input. Okay. So this is the efficiency formula, that is output by input. So this is the efficiency formula. So if you calculate the efficiency of heat engine, so we want to calculate the efficiency of heat engine, that is equal to what is our output. So in this heat engine, that is W is the output, And what is the input? So focus on that. So this is our system. So heat engine, this is our system. So heat is absorbed. So Q1 amount of heat is absorbed by heat engine, and W is produced work, and Q2 is rejected by the heat engine. So here if you calculate the efficiency, that is equal to output by input. So what is output? That is W. And what is input? That is Q1. So there is only Q1 is the input, and this is W is the output, and Q2 is rejected. So output, that is W, that is high grade energy, and input, that is Q1. Okay. Now focus on this system. This is the heat engine. So Q1 amount of heat is absorbed. So Q1 is into the system, and Q2 is going out from the system, and W is going out from the system. So if there is a conservation of equation is there from this equation. So there is a heat is coming and energy is coming and energy is going. That means you can say that so Q1 is coming, that is equal to W is going out from the system, and Q2 is going out from the system. Okay, so from this equation you can say that this is basically first law of thermodynamics. So conservation of energy. So W, that is equal to Q1 minus Q2. So here just put the value of W, that is Q1 minus Q2 by Q1. Okay, now this is equal to 1 minus Q2 by Q1. So what is this? So basically the formula, what is the efficiency formula? So this is the actual efficiency. So this efficiency is known as actual efficiency. So you can say that actual efficiency of heat engine, that is equal to 1 minus Q2 by Q1. So this formula, that is very, very important. This formula is very, very important. Now if you want to calculate the maximum efficiency, or Carnot efficiency, so the formula of maximum efficiency, if you want to calculate the heat engine Carnot efficiency, or if you want to calculate heat engine reversible efficiency, or if you want to calculate the maximum efficiency, or if you want to calculate the best efficiency or ideal efficiency, that is equal to 1 minus the Q2 is going to be T2 by T1. So this is the maximum efficiency, which depends on the temperature of source and sink. Very, very important. This is the maximum efficiency. Very, very important. Okay. So now this actual efficiency must be less than equal to maximum efficiency. So efficiency actual must be less than equal to efficiency, maximum efficiency, or you can say that Carnot efficiency or reversible efficiency, best or ideal efficiency, you can say that. So from here, so this is very, very important. So if the efficiency actual is less than maximum efficiency, then this is known as irreversible engine. Irreversible engine. Sorry, ENGINA. And if actual efficiency is equal to maximum efficiency, then it will be reversible engine. And if the actual efficiency is greater than maximum efficiency, basically this is not possible. So this engine is not possible. Okay. Now I will focus on the that is refrigerator. Second is that is first is heat engine and second is refrigerator. So we will calculate the COP, coefficient of performance of refrigerator. So we will calculate the COP, coefficient of performance. Suppose here consider this one is there is a source and the temperature of source, that is T1, and there is a sink. The temperature of sink, that is T2. Achha, one thing you should remember that in heat engine the source temperature is greater than sink temperature, so T1 is greater than T2. Okay, the absolute temperature of source is greater than sink temperature. Okay, in this here also the source temperature T1 is greater than T2. Okay, T1 is greater than T2. Now in between source and sink there is a refrigerator is there. Okay, so basically refrigerator absorb the heat from this source. Suppose Q2 is absorbed heat from this sink and it is rejected to the source, that is Q1 amount of heat which is rejected, and the work is done to the system on the system. So work is done on the system, that is considered as this is W. So that's why in heat engine the work is produced by the system, but in refrigerator we provide the work to the refrigerator. That is why we calculate the COP of refrigerator. Okay. Now if suppose this is our system, so if you apply first law of thermodynamics, so this is conservation of energy, so energy input that is equal to energy output. From this you can say that that is Q2 inlet plus W, that is input energy, that is equal to output energy. From here you can say that W equal to Q1 minus Q2. Okay. Now if you calculate the COP means coefficient of performance. So basically refrigerator concept is coming from Clausius statement. Clausius statement. Okay, so if you want to calculate the COP of refrigerator, that is the formula is cooling effect by energy input, but desire effect by work input. Desire effect by energy input. So for COP calculation of R, that is equal to what is our desire effect. So our desire effect to cool the sink. Okay, so Q2 is our desire effect, Q2, and what is the energy input or work input is that W. So from here you can say that Q2 by what is the value of W, that is Q1 minus Q2. Okay, so this is the actual efficiency, actual COP. So this is the actual COP. So COP actual, that is equal to COP refrigerator, that is equal to Q2 by Q1 minus Q2. This is very, very important. Remember this formula. Now, so this is very, very important. Now, if COP of maximum COP, if you want to calculate the maximum COP, so COP maximum equal to, you can say that, reverse Carnot. COP reverse Carnot. You can say that COP waste or ideal that is the formula. What is the formula? Just Q2, that is goes to W, and Q2 goes to T2 by T1 minus T2. Okay, so this is the formula of maximum COP. Now, this formula very, very important. Now, this actual COP always less than equal to maximum COP. So actual COP actual always less than equal to COP maximum. Okay. Now focused on last, that is heat pump. So this concept is coming from Clausius statement. So we will calculate the COP, coefficient of performance of heat pump. Okay, suppose there is a source, the absolute temperature of this source, that is T1, and there is a sink, the absolute temperature of this sink, that is T2. So consider that is T1 is greater than T2. So in between source and sink there is a heat pump, and the heat pump absorbs the heat from this sink. Q2 amount of heat is absorbed from this sink to the heat pump, and it is rejected the heat to the source by absorbing the work. Okay, so that is why we calculate the COP. Okay, so this is our system means where our study is focused. So here, if you apply first law of thermodynamics in this system, so energy input, that is equal to energy output. So from this, if you consider this system, so Q2 is inlet and W is going into the system and Q2 is outlet. So you can say that Q2 plus W, that is equal to, sorry, this is Q1, that is Q1. So you can say that W equal to Q1 minus Q2. Okay, now if you want to calculate the COP, what is the formula of COP of heat pump? COP is desired effect by energy input. This is the formula of COP, desired effect by energy input. So here, what is our desired effect? So for heat pump, our desired effect is source, that we want to increase the source temperature. Okay, we want to heat the source, our room. So this is our desired effect. So Q1 is our desired effect. So Q1 by W. So from here you can say that Q1 by W is equal to Q1 minus Q2. So this is the actual efficiency. This is the actual, COP actual. So this is the formula. You can remember this formula. Okay, very, very important. Now in COP of heat pump, that is equal to, what is the formula, Q1 by Q1 minus Q2. Now we want to calculate the relation between COP of heat pump and COP of refrigerator. COP of refrigerator, we want to calculate this. So here just in both side minus 1, that is equal to Q1 by Q1 minus Q2 minus 1. So from here COP heat pump, that is minus 1, equal to Q1 minus Q2 by Q1 minus Q1 plus Q2. So from here you can say that COP of heat pump minus 1, that is equal to Q2 by Q1 minus Q2. So from here you can say that COP heat pump minus 1, that is Q2 by Q1 minus Q2. So for COP of refrigerator, that is Q2 by Q1 minus Q2. So you can say that COP of R. So from here you can say that COP of heat pump, that is equal to COP of R plus 1. COP of R plus 1. So this formula, this equation is very, very important. So COP of heat pump, that is equal to COP of refrigerator plus 1. Okay. Now if you want to calculate the maximum COP, if you want to calculate the maximum COP, so this Q1 is converted to T1 and T1 minus T2. Okay. So now if you want to calculate the COP maximum of heat engine, that is equal to COP reversed Carnot, or if you want to calculate the COP based or ideal, the formula is, that is T1 upon T1 minus T2. Very, very important formula. And COP actual is always less than equal to COP maximum. Okay, thank you.